So we've graphed a polynomial. Now let's look at a rational. All right. So I have x squared over x squared minus 4. Now, think back to your algebra days. We're not going to take limits of this stuff to actually determine horizontal and vertical asymptotes. We figured it out as to why we can do it, but let's use what we know. That just works out better. So if I have a horizontal asymptote, do you remember the rules for horizontal asymptotes? Yeah, if you have a leading coefficients, so the degree is the same, you're going to take those leading coefficients. I have 1 over 1. Good, so then that's going to be a horizontal asymptote at y equals 1. What about vertical asymptote? Yep, set that denominator equal to 0. You're in Calc 1, so I can expect you to do this in your head. If you have this difference of squares, when you factor that, what do you get? Plus or minus 2. Good. So x is equal to a positive 2 and x is equal to a negative 2. As soon as you know some values here, go ahead and put those on your graph. So I know y equals 1. There's my horizontal asymptote. I'm at negative 2 and positive 2. All right? Okay. Now, let's do some first and second derivative testing here. Here's our first derivative. Let's go black on it. So, in order to have a first derivative test, you have to take a first derivative. So, let's do it right now. F prime of x, I've got the quotient rule. So the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right. Then go ahead and distribute this and clean it up. So f prime of x, if I distribute this here, and those are multiplied, I've got 2x cubed minus 8x minus a 2x cubed. Well, that's handy. Check that out. X squared minus 4 squared. The 2x cubes cancel. Oops, let's go black. So my first derivative is negative 8x over x squared minus 4 squared. Now here's the deal. Here's the deal. When you're finding critical values, there are two criteria, right? Set it equal to 0 and where it's undefined. Good. So two things we're looking for here, where I set it equal to 0 and where it's undefined. So if I want to find my critical values, I know that x is equal to 2 and x is equal to a negative 2 because this is where it is undefined. That's where my denominator is equal to 0, right? And remember, when we're setting this up, you only have to set the numerator equal to 0 because the denominator always zeroes out. So now I have x equals 0. I have 3 critical values here. And so I need to use all 3 of those when you go to set up your interval. So let's do it. I'm going to scoot this up so I can see it a little bit better. So we have an interval. I want to say, where's my first derivative? Either positive or negative. And then that's going to tell me increasing or decreasing. I want to know, is my graph increasing or decreasing? That's so important, especially with rational. It is so important. I don't know how to get that across from you. And you'll see why here in a second. It does more than just determine where my graph is. So I'm going to go to negative 2. Negative 2 to 0, 0 to 2, and 2 to infinity. So you have to hit all of them. Okay, let's do it. So make your life easy. Let's go with negative 3. Again, I am plugging this in. So if I plug a negative 3 in, look at what happens if I plug anything into the denominator. This is going to be squared at the end of it. So every single time, no matter what I put in here, even if this comes out negative, when you square it, it stays positive, right? Yeah, so use that number sense. When I plug in a negative to my numerator, though, What's a negative times a negative? Positive over positive is going to be positive. So my graph is increasing. Good. Now, what's between negative 2 and 0? Oh, how about a little negative 1 action? Again, we know the denominator, is always going to be positive because we just talked about that. But whenever I plug a negative 1 in here, a negative times a negative is going to be positive. Good, which is equal to positive, and my graph is increasing. All right, f prime of 1. I'm going to take a 1 and plug it in. Obviously, that is a positive. When I take 1 and plug it in here, negative times a positive, it's a negative. Good. So negative over positive is negative. My graph is decreasing. Last but certainly not least, let's plug in a 3. So negative times a positive is a negative. So my graph is decreasing. Now, what do we know from the very beginning? What is happening at negative 2 and positive 2? Yes, vertical asymptotes. That doesn't change. That doesn't change. My graph does not flatten out there. If I'm decreasing to decreasing, if it were a continuous graph, we'd have a different conversation. This is a rational graph. I already know where the asymptotes are. That's why we find those up front. So now I'm looking at this. Those are vertical asymptotes. Label them as such. Then my graph is increasing to decreasing. Yep, that's going to give me a maximum. So I now have a max at x equals 0. So plug a 0 in where? To your original function. Yep. F of 0. Let me squeeze this back so we can even see what the original function is. Gives me 0 squared over 0 squared minus 4. And that's 0. So I have a point here at 0, 0. And I know that's a max. So I like to just put a little hump right in there. So I know then that's maximum. Okay. Now, let's try a little second derivative test action. So from my first derivative, which right here is good, I'm going to do a second derivative. I have this paper, this big graph paper, uploaded in the course. I would highly recommend you using that because that is super helpful. So my second derivative is derivative of the top, which will be negative 8 times the bottom, which is x squared minus 4 squared, because that's still the whole bottom, right? Minus the top, which is a negative 8x, times the derivative of the bottom, where we get to use chain. So derivative of the outside, keep the guts, then you have to multiply by the derivative of the inside, all over the denominator squared. Oops, I don't know where that plus sign came from. Something squared is to the fourth. Now, this, ladies and gentlemen, is why we learned factoring. Look at what's happening here. I've got a group of x squared minus 4 and a group of x squared minus 4 here. Let's take care of business, right? I've got another one right here. I can cancel and simplify that. So if you notice groups that are in common, because this is all multiplied back here, that's a whole term. This is a whole term. Factor out that x squared minus 4. I'm going to scoot this up so we can see it better. And that leaves me with a negative 8 times an x squared minus 4, because I only factor 1 out. Here, I'm going to multiply those negatives together so I don't have to think about them. This x squared minus 4 factors out, but I've got 8 times 2 times 2x. So that's going to be what? Plus a 32x squared all over x squared minus 4 to the fourth. That one takes that one out, leaves me with 3. I can distribute. My second derivative here is going to be a negative 8x squared plus 32 plus a 32x squared over x squared minus 4 cubed. And then those are like terms, aren't they? So my second derivative is going to be, what's 32 minus 8? 24. Now I'm going to factor this out to have my second derivative just because it's easier. Can we take an 8 out of that? And so then I have a 3x squared plus 4 all over x squared minus 4 cubed. All right. All right. Now let's talk about critical values. What do you automatically know is happening there? Yes, that denominator if I have critical values. Remember, critical values come from where I have undefined and where it is 0. So for my critical values, I know x is equal to positive and negative 2. Now let's talk about this numerator here for a second. Is there absolutely anything I could plug in there that would make that that would set that equal to 0? No. Do you see that? Nothing. No, oops, I already had it. Nothing here. This is positive. It has to be positive because it's squared. I'm going to add more to that, positive numbers. Is there anything I can do to bring that back down to 0? No. Just for grins, let's go over here and I'm just going to show you real quick. I've got 8 times a 3x squared plus 4 equals 0 divided by 8, right? So 0 divided by 8 is still 0. When I subtract 4, you get 3x squared is equal to a negative 4. So x squared is equal to a negative 4/3. What happens when I take that radical? Yes. All of a sudden I start having imaginary numbers, right? I can't have some imaginary number. That's not going to work. So that does not count. The only critical values are positive and negative 2. Okay, so I'm going to build my chart off of those critical values. I'm actually going to change my colors. Oops, I'm going to go blue because we're kind of getting jammed up here a little bit, aren't we? So I'm going to put this line down here. I have an interval. My second derivative is either positive or negative, and that's going to tell me if it's concave up or down. I'm going from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Let's see what happens. And right now we already know that we've got a vertical asymptote and a vertical asymptote, right? I have 0 inflection points here. We know right up front that we have vertical asymptotes. However, you're not just finding those points, right? You're actually looking to see what is the behavior of my graph. So I want to know, is it concave up or down? That helps me graph it. Oops. So I want to plug in something that works. So like a negative 3. The only thing I care about is if it's going to make it positive or negative. Now, didn't we just talk about how there's nothing in here that's ever going to make this negative? My numerator is a positive. This will always be positive plus more positive. My numerator is positive no matter what. The question is the denominator. If I plug this 3 in, that's going to give me a 9. And 9 is bigger than 4. So I have a positive divided by a positive, which is positive. Here, I'm going to circle that so you can actually see it. So I know that this is concave up. Now, let's look at what 0 is, because that's just easy. Again, it doesn't matter what I plug in here. It's always positive on top. Over. Now, if I plug in this 0, this is a negative number to an odd exponent. That's negative, folks. So a positive divided by a negative, that's a negative. So then this is concave down. The whole thing is concave down. My second derivative of 3 So let's plug that in. Obviously, positive on top. That's going to give me a 9, which is bigger. So positive divided by a positive is a positive, and I'm looking at concave up. Now let's talk about how this looks. I know if I'm coming up here from negative infinity to negative 2, right? My graph is increasing, so my graph has to be going up. From negative infinity to negative 2, my graph is going up. This tells me it is concave up. Can I have something down here? No, it's going to run right into that asymptote. That's not going to work. The only possible way I can have this concave up and increasing is if my graph is up here in this part. That's why it's so important. It's concave up. It is increasing. It has to go there. That's the only place for it. Then I look over here and I say, okay, my graph is going to increase, then decrease, and the entire time from this whole section, I'm going to be concave down. Ooh, guess what? I'm increasing to decreasing, and the entire time, I'm concave down. Cool, right? Yeah, it's so exciting. It is awesome to see how these things work out. Okay, over here, I know that I'm decreasing. That means I'm going down. My graph's going down somehow. And I'm concave up. So I have to be going down, but concave up. I can't go down and concave up down here. It doesn't make sense, right? And you know something about rational functions. Whenever you're looking around those asymptotes, then your graph lines up nicely with those asymptotes. That's kind of a janky graph, isn't it? Let's try that one again. It's curved as we go in there. The behavior of the graph is just as important or more important than finding just those points. We literally graphed one point out of this whole graph. One specific point. Everything else came from graph behavior. So you have to have these charts. You have to show what these intervals are and what the behavior of the graph is. That is important to the first derivative test, increasing, decreasing. Important to the second derivative test, concavity. Makes an impact. All right.